Hello, my name is Zach Frakestead, and I'd like to talk to you about some joint work with Chaitanya Swami on a constant factor approximation for directed latency in quasi-polynomial time. The minimum latency problem is much like TSP in that we have to visit a collection of clients with a vehicle, but instead of minimizing the cost of the tour, we want to minimize the average or total waiting time of the clients. More precisely, given a complete directed graph G over a set of clients V plus subdepot R, throughout we're going to let n denote the number of clients. We also have non-negative travel costs CUV between any two points U and V in the metric. And we want to find the Hamiltonian path P starting at the depot, minimizing the total waiting time of the clients. So C sub P of V is the cost of the RV subpath of P, the time that V waits to be served by path P. I said metric because we're going to assume the triangle inequality. The cost from U to V is the cheapest path from U to V. But we don't assume symmetry. In general, the cost of going from U to V could be different than the cost of going from V to U. Now, one key difference between latency and TSP is that an optimum TSP path solution can be a terrible approximation for the latency objective. In this simple example, the clients are located on the number line with the depot at the origin. And the clients are at geometrically increasing distances from the origin, but alternating to the right and to the left. An optimum TSP solution goes down one side and then back and then visits all of the clients on the other side of the origin. But this is the latency of this solution, though, so the total waiting time of all clients is omega of n times 2 to the n, because half of the clients are waiting time 2 to the n for the vehicle to complete its traversal of the first side. A better solution for the latency objective is to zigzag back and forth and visit the clients. You can prove by summing a geometric series that the waiting time for client I, located at 2 to the I, is O of 2 to the I, so the total latency is O of 2 to the n. But still, we can use TSP ideas to get good approximations. So for example, in symmetric metrics, so the cost from U to V doesn't depend on the direction of traversal, there's a nice idea that bootstraps approximations for k-TSP path to latency. So this is finding the cheapest path that covers k clients. Of course, starting from the depot. So suppose for any k, we can find or even approximate a shortest routed path visiting k nodes. Well, then the total cost of these paths is O of the optimum latency, because the kth client that's visited on the optimum latency solution, that subpath is a candidate solution for the shortest path visiting k nodes. Now, if we stitch a subsequence of these pi whose costs increase geometrically, then we get a good solution for latency. And the reason is that if you visit one of these paths, then you can then return to the depot and get ready to visit the next path just by, well, the cost of going from the end of one path to the depot is bounded by the length of the path because it's a symmetric metric. So it's not too hard to show. If you do something like this, you can get a solution whose latency is O of the sum of all the path lengths. Now, an elegant refinement of this approach yields the current best approximation of 3.5912 for symmetric latency. But in asymmetric metrics, there are two key barriers to making this approach work. One is that no constant approximation for k-TSP path in asymmetric metrics is known. The best is polylogarithmic so far, and even considering the new constant factor approximation for ATSP. Now, even if we could approximate asymmetric k-TSP well, we can't just stitch the paths together like before. We can't return to the root after one path is finished. At least we don't know how to bound the cost of doing that. So perhaps the most relevant previous work on directed latency is this log n approximation from 2010. And this work uses an RLP relaxation to find paths that collectively cover all clients and their costs are geometrically increasing. and the sum of the, well, not just the total cost of the paths, but in fact, the cost of the paths times the number of clients covered by the path. That sum is at most log n times the optimum latency. So this relied on an Atsp path integrality gap of log n that was also established in this work. But it wasn't just the integrality gap that lost a logarithmic factor. A second logarithmic factor was lost additively to pay for the stitching. The LP constraints and variables were leveraged to show that the cost of stitching pi to the first client on pi plus 1 was bounded by O of log n times 2 to the I. Now, more recently, Post and Swamy consider LP-based approximations for undirected latency via time-indexed LP relaxations. And I'll talk about what this means later, because we build off of this time-indexed relaxation for our result. So in their work, they get improved approximations for multi-depot and vehicle minimum latency problems. But of interest also is the fact that they get they recover the 3.5912 approximation for minimum latency in symmetric metrics, but with an LP relaxation. Okay, so our main result is a constant factor approximation for the directed latency problem with running time n to the O of log n, so quasi-polynomial time. An important technical aspect of our work is we need to generalize the constant factor integrality gap bound for Atsp path to a slightly different setting. So if what we show is that if you consider the standard Held-Karp relaxation for Atsp path, this is a standard relaxation, but then replace the cut constraints, saying the inflow is at least 1, instead to the inflow is at least some value rho, where rho is between 1/2 and 1. Then we show the integrality gap bound is some constant times 1 over 2 rho minus 1. And we also show this as asymptotically tight with a simple example whose gap is, that should be 1 over 2 rho minus 1 for any such rho. We also consider a restricted but interesting setting for directed latency. So the constant in our approximation is very large. It's in the thousands. We do get better bounds in regret metrics. Now suppose first that the distances are symmetric. Given a path, let's define the regret latency of a client on this path to be the distance along this path to the client minus the shortest path distance to this client. So this is the time the path spends in excess of the shortest path distance to V. This is a little natural because clients might be understanding that if they're far from the depot, then it takes time to reach them, but they could be frustrated by additional waiting time beyond this shortest path time. So more concretely, given some distances C, if we define these regret distances C reg as you see on the screen, then it's easy to show that this forms an asymmetric metric even if C is symmetric, and that the regret distance along a path according to these new distances is equal to the original distance of the path minus CRV for any path that starts at R and any V on the path. Now what we show is there's a 397 approximation for directed latency with running time n to the log n again in regret metrics that stem from symmetric distances C. While still very large, conceptually we see it seems easier to get approximations, better approximations in this setting than in general directed metrics. And we use techniques from earlier work in regret-bounded vehicle routing to pull this off. But for the remainder of the talk, I'm going to focus mostly on the directed latency approximation that assumes that our gap bound for the slightly relaxed Atsp path LP relaxation. And then the last little bit, if you're interested, is that we sketch the gap bound for Atsp path. So RLP relaxation uses a time-indexed approach. So first we have variables for every client in every time t, and these xvt variables indicate if client v is visited precisely at time t. One can assume that all the distances in the metric are integers that are bounded by a polynomial in n, by losing an epsilon in the approximation guarantee, so we make this assumption. Second, we have variables indicating when edges are traversed. So zet indicates we finished traversing edge E at time exactly t. So that's the end of we're done traversing E at time t. Now the LP is a bit big, but let me talk this through. The objective function simply is for if a client V is visited at time t, we'll add t to the objective function. So this will be the total latency of all clients, the total waiting time of all clients. And the constraints say, first, every client is visited sometime. Second, the path exits the route at time 0. Third, the vehicle enters a set of nodes S by time t if any client in this set is covered by time t. So this is like a generalization of the classic cut constraints from vehicle routing. And finally, the vehicle only leaves leaves a client at time t if it reached the client at time t. You can't leave the client unless you enter it. This is kind of like a flow-like constraint. In fact, it's more like a pre-flow type constraint. Okay, so here's our strategy. First, for every client, let's let TV be the earliest time index t, such that V is at least 2/3 covered by the LP. And this is a good proxy for the actual contribution of V to the latency objective function. So in particular, suppose we have a latency solution P, where the latency of V along P is O of this TV value. Then the claim is that the total latency of P is in fact a constant approximation to, then P provides a constant approximation relative to the LP. And the proof is quite simple. By our choice of TV, at least 1/3 of the LP mass for V, so the XVT variables, at least 1/3 of them is for times at least TV. So that means TV is at most 3 times V's contribution to the objective function, and it's that simple. On the other hand, we see that V will be at least 2/3 covered by point TV, and we're going to exploit that to make sure that that we cover V by time approximately TV. So how do we do that? How do we cover V by time approximately TV? First, we consider bucketing the clients. So we consider buckets from 0 to k being O of log n. Really, it's a log of the maximum possible time index. And a client is in bucket I if its TV value is between 2 to the I and 2 to the I plus 1. So it's important to remember that a client is in bucket I if TV is, if its fractional latency is O of 2 to the I is the important part. Now we see in this picture, I call this the time expanded graph. So node in this picture corresponds to both a client and a time. So it's a client comma time pair. And time goes from left to right in this picture, and a client itself might be represented at multiple nodes. This is just indicating that a client is visited to some extent by the LP, and the dashed edges represent the ZET values. So we see this client V is highlighted in the picture a few times. It could appear multiple times in some buckets or 0 times in some buckets, but we've emphasized the last dark green depiction of V as being the time when the total XVT value up to that time t is at least 2/3. So then V lands in this bucket. This is finally when it's 2/3 covered. So what we're going to do is for each bucket, we're going to cover all clients in the bucket with an R-rooted path of cost O of 2 to the I. So that will solve half of our problem. We'll get these paths, these geometrically increasing paths. The cost is geometrically increasing, and that will collectively cover all nodes. We'll deal with stitching later. But first, let's see how we actually get these paths. Why do we argue that a good path exists? So the restriction of the variables z to times at most 2 to the I plus 1 constitutes an R preflow of cost 2 to the I plus 1, such that the RV connectivity of each client in this bucket I is at least 2/3. Now concretely, we mean for any edge E, if you sum its z values for all times up to t, that sum should be over z e t prime. And then you can easily show that YE forms a unit of preflow, which is like a flow. It's just that you have in degrees at most out degree at every node. And the RV connectivity for any client in the bucket BI is at least 2/3. Oh, and also the cost of this preflow is at most 2 to the I plus 1, just because the cost of an edge is equal to the distance it hops in the time expanded graph. So what we want to do is we want to restrict this preflow to only span nodes in the bucket plus the depot. So using splitting off techniques, we can do this. This is like kind of like a classic shortcutting of a path to get around a node. So if you haven't seen this before, what this allows us to do is this allows us to take a node that's not in the bucket and bypass all preflow heading into it by taking an incoming arc and an outgoing arc, and then just shortcutting the flow to just the direct hop. By the triangle inequality, that doesn't increase the cost, and Mader showed that one can do this in a way that ensures all other nodes have their connectivity from R being preserved. So now we have a preflow emanating from R and spanning BI, and it also is 1 unit of preflow. We can complete this to a proper flow like this just by adding an auxiliary vertex with zero cost edges coming into it. And now we get an RR prime, 1 unit of RR prime flow spanning all of BI. And it's like an Atsp path solution with connectivity at least 2/3. So not quite connectivity 1, but at least 2/3. So a sizable part of our paper is extending previous work on rounding Atsp, the Atsp path LP. But we have to show that one can bound the integrality gap of this slightly weaker relaxation with 2/3 connectivity. So, and by and large, most of their ideas carry through to this general setting, but we need a new idea for one part, and I'll discuss this at the end. But for now, let's just assume that the gap for this slightly weaker Atsp path LP is bounded by a constant, which means we can find a path PI from the depot spanning bucket I with cost O of 2 to the I. The preflow that we created and then turned into a flow witnesses a good Atsp path LP solution, and the constant gap ensures we can get an actual path. And of course, this is obtained with a polynomial time algorithm. So for each bucket, we consider the path. Now we're going to, if we consider traversing the paths in order, always going from the end of one path to the first client of the next, this would give us a feasible solution spanning all clients. The problem is we don't know how to bound the cost of, we'll call this the stitching edge, from the end of one path to the first client on the next. And we couldn't see how to give any good bounds on this given just the current LP, and this is where we involve quasi-polynomial time. We're going to further strengthen our LP relaxation by guessing some things. So what do we guess? So consider every geometric window in the timeline. Suppose we know the last vertex visited by the optimum solution within this time interval. And even further, suppose we knew the exact visiting time of this node in this interval. We're going to strengthen the LP with this knowledge. So we're going to say that Vi star is visited at time exactly Li star for each bucket I. And we're also going to forbid any other node being visited between Li star and the end of this time interval, 2 to the I plus 1. Now, of course, there might be some buckets for which the optimum solution visits nothing. So some time intervals for which the optimum solution visits nothing, but that's easy to handle. It's a mild technicality. Let's just assume that doesn't happen for the sake of simplicity in this presentation. Note there are n to the O of log n guesses, because for each of the log n buckets, remember there's log n, O of log n different time intervals because the maximum time is polynomial in n. So there's log n of these different time intervals. Each you have to guess one of n different nodes, and the time, Li star, which is going to be bounded by polynomial in n as well. Okay, so what does our solution now look like when we have this guess? Well, you can see in this picture, in the time expanded graph, all of this Z flow enters the last node from each bucket. And then all of the flow moving into another bucket comes from the last node of the previous bucket. That's intuitively what's happening. And what we then prove is then with this property, the edge from the last node in bucket I to the first client of the path of pi plus 1, in fact, for any client in the next bucket, one could prove, has cost at most 2 to the I plus 1. And this isn't so bad. So when we're considering this time-expanded graph, let's be precise now. The vertices are, again, v comma t pairs, client comma time pairs. And we have edges from ut to v t plus cuv. The z variables of the LP naturally correspond to 1 unit of flow in this graph, starting at r at time 0 and ending at v star k at time l star k. You can prove fairly easily that with this guess, we're now forced to have an actual flow, not just a pre-flow. And again, like I emphasized earlier, all units of flow pass through every vi star li star pair. So for any node in bucket I plus 1, any client in bucket I plus 1, the flow in the time expanded graph does support a vi star li star to ut path for some t in the most 2 to the I plus 1. And this is because since u lies in the bucket b I plus 1, it is supported to some positive extent in this bucket by the LP. So then for flow to reach it, it would have to pass through vi star at time li star plus li star 1. So this path in the time expanded graph, it maps back in the original graph to a vi star u walk with cost at most 2 to the I plus 2. Therefore, the stitch from the end of pi to the first client of pi plus 1 has cost at most 2 to the I plus 1. Now the stitches are bounded. So the final latency of some client v in some bucket bi is then, well, the cost of all the paths up to this bucket's path, plus the cost of the stitching edges, where the stitching edge from the ith path cost O of 2 to the I. Remember, C of pi is O of 2 to the I as well, so the total latency of V on this final stitched together path is O of 2 to the I, which is O of its TV point. And that's it. So final comments on this algorithm is, well, first, our integrality gap bound for the weaker Atsp LP relaxation loses constants much worse than what's lost in previous work. It's because we've chosen simplicity in presentation over optimality of the constants, and partially because even if we did optimize, we would have a very large directed latency approximation. But there are some things that get a bit more tricky in our settings, so it was easier just to keep the presentation simpler. So thanks for listening to this part of the talk. If you're interested, you can stick around for a few comments on our Atsp path LP bound, but the main ideas for the directed latency approximation have been presented. Thank you. Okay, for the Atsp path LP relaxation, we consider the following LP. So from now on, we're not thinking about the depot R, we're just looking for an ST Hamiltonian path in some asymmetric metric, and X is now going to refer to variables from this relaxation. So we want to minimize the total cost of all edges used in our path, subject to the fact that the X values form 1 unit of ST flow, and for any set U that doesn't include S or T, well, you know intuitively, since nodes into the set have to be visited, one edge enters, one edge exits. So the standard relaxation says the total weight assigned to all edges entering and exiting is at least 2, but we have to bound it for at least 2 times rho. So what we do is, like previous work, we consider the support of an optimum solution to RLP. We complete it to a circulation by pushing 1 unit of flow from T to S along 2 auxiliary back edges, with total cost being the optimum LP solution. Then X star rho is a feasible Atsp cycles LP solution with cost O of RLP optimum. Because the integrality gap for Atsp cycles is constant, we find a Hamiltonian tour with cost O of our optimum LP solution. And if we delete all occurrences of the 2 back edges, of which there will be at least 1 occurrence because we spanned T prime, we get some ST walks of total cost O of opt LP, which collectively span all nodes. And also the number of these paths is constant because every time we delete one of these back edges, we're removing opt LP cost from our solution. So we have a constant number of paths that collectively span all nodes, and their cost is bounded by O of our LP optimum. Next, consider the strongly connected components in the support of X star, our optimum LP solution. And look at the restriction of the paths we just found to these components. Don't worry about the edges that hop between components. That's what's depicted in this picture. The large circles are the strongly connected components. Unlike the case when rho equals 1, it's not necessarily true that all paths intersect all components. Some paths may hop over some components, hop past them. Well, we take a simple approach, which is probably not optimal for constants, but at least demonstrates that the gap is bounded as we need. For each component, what we simply do is we stitch the end of each subpath to the start of the next subpath in any order. You look in the components here, and we stitch them together in some order. It doesn't matter. Now, as long as you stitch them together via shortest paths. Now, elegant duality arguments from previous work carry through identically to this setting, and essentially show that the total cost of all stitches across all components is bounded by the LP optimum. There's a small caveat to that I'll mention, but it's okay to think of that for now. And what we're left with is this circuit in each strongly connected component, and the circuit spans all nodes. So next, we're just going to chain these circuits together to get our final Hamiltonian path. And this is where our work diverges the most from previous work. It's not necessarily true even that every edge of the support of X star goes from one component to the next according to some topological ordering of components. Remember, these are the strongly connected components. It could be that some edges jump over some components in this ordering. But we prove that there's a reasonable amount of LP mass between consecutive components, enough to witness the fact that if we just pick the cheapest edge between consecutive components, this will suffice to get our bound. So if you consider topological ordering of the strongly connected components, we show that the total LP weight, like the total X star, going from Ci to Ci plus 1 itself, not hopping over, is at least 2 rho minus 1. Now, if we can do that, then it means if you pick the cheapest edge going directly from Ci to Ci plus 1, you can charge it to 1 over 2 rho minus 1 times the LP cost in this region. So you pick the cheapest edge as bridging consecutive components, do this for all components, and the total cost of those connecting edges is the opt LP over 2 rho minus 1. And there we get our final Hamiltonian path. Start from S, hop to the next component, traverse the circuit, and then traverse it again up until the exit edge. Follow the exit edge and repeat. Now, the one caveat here is that we said completing each component to a circulation costs essentially O of opt LP due to some duality argument. If you know about the previous work on Atsp path, you know that there's one other bound you have to provide, and we have to provide it too. You have to bound AS minus AT, where in general AV is the dual variable for the flow conservation constraint for V. Previous work bounds it by opt LP with another very nice argument using duality, and one could adapt this proof to our setting to show that it's at least bounded by opt LP over 2 rho minus 1. But if you're interested, we give a slightly different proof of this fact using complementary slackness with a new auxiliary LP that we defined for the argument. They're essentially saying the same things, their argument and ours, but ours just provides maybe a different perspective. So in total, we construct a Hamiltonian ST Walk with cost O of opt LP over 2 rho minus 1 as we require. Now the final slide here, I'll just leave this up. You can pause the video and look at it if you want. This is just showing that our analysis is asymptotically tight as rho approaches 1/2. Thank you very much.